Welcome to the end of our Section P2 lectures. This time we're just going to be taking a short look at some exercises from P2. We'll just do a few of them, and I think we should be over with it fairly soon. So this shouldn't be an extremely long video. I will also add annotations to the video so you can see what problems were done in the video, and that way you might be able to skip to some of the problems you actually want to see. Alright, let's get started. This is the first problem we're going to be looking at. This is from Section P2. It's exercise 7 on page 15 in our book. And what we have here is a set of numbers, and we are going to list which of these numbers are natural, integers, rational, or irrational. Now in this problem you can actually save some time if you remember that the first three are nested. All natural numbers are integers, all integers are rational numbers. It's easier to start with natural numbers and then just copy down as you go. Let's try that. Let's start off with A, natural numbers. I'll draw myself a little curly brace here to start off. Natural numbers. Natural numbers are the counting numbers, if you recall, and they start at 1. That's a negative number, so that isn't positive, so it can't be natural. The natural numbers start at 1, so 0 can't be 1. That is not a whole number. Square root of 7 is not a whole number. That's a decimal. That's not a whole number. 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 So there's actually no natural numbers in that set. So what I'm going to say there is I'm going to say the empty set. The integers, let's see, we have -3. We have 0, and let's see, any other, -1000, that's definitely an integer. So, all integers are rational numbers, so I can start off with all three of those. Give myself a curly brace. -3, 0, -1, 0, 0, 0. Rational numbers are any numbers that can be written as a fraction with an integer on the top and bottom. 22 over 7, that's an integer, so it is a rational number. 22 over 7. Square root of 7 is not rational. It's an infinite non-repeating decimal, but just by virtue of the fact that it's a root that doesn't simplify to a whole number, or at least a rational number if you plug it into the calculator, it's not going to be rational. That was actually one of the big sources, we said, of irrational numbers was irreducible roots. 3.14, even if you didn't remember from our definition of rational numbers that rational numbers had finite length decimals or infinite repeating, you can always convert finite length decimals to fractions very easily. You just read off the last decimal position place. So tenths, there's 1/10 and 4/100. Therefore the number is equal to 314, just all the numbers, over what was the last place? Hundredth, so 100. Integer over integer, sure you could reduce it at this point, but just this makes you know it is a rational number. So 3.14. And what do we got left? Negative pi. Pi is very famously an irrational number, so we're not doing that. 2.76 continuing. As we said, infinite repeating decimals are rational. So 2.76 is rational. And then -2/5, integer over integer. So that is rational. Once you've got all your rational numbers in place, the irrational numbers are easy because they're all that's left. We already crossed out all of these. We crossed out 3.14. We crossed out 2.76 continuing. Crossed out -1000. And we crossed out -2/5. So all that's left is the square root of 7 and negative pi. That's the entire set. Empty set, negative 3, 0, and negative 1,000. Same set plus all of these extra numbers, and then square root of 7 and negative pi. For our second problem, we'll be looking at exercise 46 from the same section on page 15. Now in this problem, we're writing all of these statements in terms of inequalities. Alright, y is negative. Well, if you think about that as an inequality, the inequalities we have are less than, greater than, less than or equal to 0, and greater than or equal. So if we want to say y is negative, well, the boundary for negative numbers is 0. And if you want to be negative, you have to be less than 0. So that's the answer for part A. Part B, z is greater than 1. Well, that's about as on the nose as you can get, because we actually have an inequality for greater than. So z is greater than 1. B is at most 8. If you think about what at most means, it means it can't be more than, but it can equal. So if you can't be more than something, you have to be less than or equal. W is positive and is less than or equal to 17. There are two ways of writing this. The simplest way is to write it as a compound inequality. We know it's less than or equal to 17. And we know it also has to be greater than 0, so we can write it that way as well. Or you could write it as two inequalities and put an and in between. And is an acceptable statement in mathematics. It means both of the conditions have to be true if this statement is going to be true. So that would work as well, but obviously the compound inequality is a little bit shorter. So it's really up to you. Y is at least 2 units from pi. This is probably the most missed problem in the homework for this section. The idea here is that you have to talk about the distance between these 2 units. And whenever people are doing problems where they have to interpret mathematical language, a lot of times if you take away the variables and replace them with names, people have a much better grasp than they think. Because math is all about quantifying the way you think on paper. Because once you can put it on paper, you can improve it. Improve the process. So, let's think about this. If I'm Y, so if Paul is Y, and someone else is, say, Harry is pi, so Paul is at least 2 units, we'll call it inches. Feet. I don't want to be that close to Harry. Paul is at least 2 feet from Harry. Well, that means the distance between Paul and Harry is at least 2 units. Well, I can work that out. The distance between y and pi is at least 2. Well, we already know how to say the distance between y and pi, if you watched the end of the last video anyway. The distance between y and pi is the absolute value of y minus pi. And then at least 2, well, we talked about something similar to that in C. To be at least something, you have to be greater than or equal So y minus pi is greater than or equal to. And we're good. Let's go to the next problem. In this problem, we're expressing this inequality in interval notation, and then we're graphing it on a number line. I'll express it in interval notation, then I'll actually go to another program to graph on the number line. We're looking at -2 to 1. Let's see here. -2 is the left endpoint. 1 is the right endpoint. -2, since it's a strict inequality, I can't actually equal, should have parentheses. And 1 should have a square bracket. For the graph, if we're going to go from -2 to 1, I would have a filled in... Oh, that's wrong. It was strict inequality on the -2, so should have an empty circle on the -2, a filled circle on the -1, just like that. Although I suppose I should actually graph it on the line itself. And that's the graph on the number line. Graph the set, and I just brought up my number lines down here so we could graph on this set. So this is a union of two intervals, but that's not any harder to deal with because remember, union just means everything in either set. So we have one that's going from -infinity to 6. Okay, so -infinity. Yes, these sound effects are necessary. To 6. And then 2 to 10. Alright, that's the two graphs. Now the union would be the combination of both sets. So if you see here, if we dump everything in either set, then we will have everything from here. I think I'm going to go ahead and continue graphing above, just because, so I don't have to make a really thick line across all of it. Let's see, and it will continue all the way out to 10. And it shouldn't include 10 because there's a parentheses on 10. And that should be the whole set. So this is the answer. The top is just scratch work. And that'll finish us off on this lecture and this section. Hope you enjoyed the lesson. Come back for P3 when we talk about exponents.